In this section, we're going to be looking at bond strength, and we're going to be focusing on covalent bonds right now. Bond strength describes the energetics of covalent bond formation and breakage. The bond strength is how strongly each atom is joined to another atom. So, how much energy is required to break the bond, or how much energy is released when the bond is formed. Bond dissociation energy is also called bond energy. It's a little shorter. And it is the energy required to break a specific covalent bond in 1 mole of gaseous molecules. And if we were to add up the sum of all of the bond energies in a molecule, it should equal the standard enthalpy change for the endothermic reaction that breaks all of the bonds in the molecule. So if we add up all of the energy it takes to break the individual bonds, we should get the amount of energy it takes to break all of the bonds. In general, the more electrons involved in a bond, the stronger the bond will be. If you think about it, if there's more electrons, the nuclei are going to have a stronger attraction for the electrons in that bond, which is going to cause the bond not only to be stronger, but also shorter in length. For example, a carbon-carbon single bond takes 345 kilojoules per mole to break. If I have a double bond between carbon atoms sharing 4 electrons, those nuclei have a stronger attraction because now there's 4 electrons in between that they're attracted to instead of just 2. And it takes 611 kilojoules per mole to break that double bond. Now that is talking about breaking both of those bonds in the double bond, not just one of them. And then if I have a triple bond between 2 carbon atoms, it's even shorter because now there's 6 electrons that it's attracted to, and it takes 837 kilojoules per mole to break the triple bond between carbon atoms. When one atom bonds to various atoms in a group, the bond strength typically decreases as we move down the group. Because as we move down the group, the atoms get larger, so those bonding electrons are farther out, the strength isn't as big, so it's easier for that bond to break. It's going to take less energy. So if we look at the carbon atom bonding to fluorine, chlorine, and bromine in group 17, carbon bonded to fluorine, which is at the top, has a bond dissociation energy of 439 kilojoules per mole. As we go down to chlorine, since chlorine is bigger, that attraction is weaker, so it only takes 330 kilojoules per mole to break that bond. And carbon to bromine, again, even bigger atom, takes only 275 kilojoules per mole to break that bond. So the enthalpy, the delta H for the reaction, is approximately equal to the sum of the bond dissociation energies for all of the bonds broken minus the sum of all of the dissociation energy for all of the bonds formed. And there should have been a D in there. If we take a look at the equation, H2 plus Cl2 yields 2HCl gas. We can write this out with all of the bonds showing. So we have hydrogen bonded to hydrogen in the reactants and chlorine bonded to chlorine in the reactants. And then in the products I have 2 hydrogen bonded to chlorine. So the bonds broken would be the bond between the hydrogen and the hydrogen, of which there's 1, and the bond between the chlorine and chlorine, of which there's 1. So if you look up those bond dissociation energies in your textbook, the energy to break the hydrogen-hydrogen bond is 436. To break a chlorine-chlorine bond is 243. So you'd add those together and then subtract the bonds that are being formed, which would be 2 of the bonds between hydrogen and chlorine. So minus 2 times the bond dissociation energy for hydrogen and chlorine is 432. and we end up with negative 185 kilojoules for the delta H value for this reaction.